Okay, so today we're going to talk about dealing with events in Bevy 0.16. And roughly speaking, there are two ways you can deal with events. You can either use event writers and event readers, or you can use hooks and observers. Right off the bat, if you have to choose between them, if you need to do batched event processing, that means you need to process multiple events in one function at the same time, you're going to have to use an event writer or an event reader. As shown in a number of examples in the docs, if you have an event reader, you can call read on that event reader and process all of the events that have been sent this frame. So if you need access to all events in the same function, event reader, event writer. Otherwise, your default is probably going to be observers, or at least one of hooks or observers. Observers also process events, so you get to be able to trigger these events and then have functions that will handle them, but these functions will run once every event. So going back to that batching thing, observers won't be able to batch process events, but that probably doesn't matter for the vast majority of use cases that you're thinking of. So as usual, we have a series of code examples that we're going to go through here, detailing different features. We're going to start off with hooks. And I've already run and stopped the Bevy program on the left-hand side here. So these are the logs for the program that we are actually going to look at. So the very first thing I want to mention is when you have component hooks, these component hooks are going to be defined where you define your component, where you derive component. There are other ways to attach component hooks to a component, but we're going to stick with the attribute macro for now. You can write them like this, all in one attribute macro, or you can write them all separately like this. It really doesn't matter. For these examples, we're going to have them each on a different line. So currently there are about 5 events you can listen to for component hooks. So define your component, make it a component, derive component for it, and then define on add, on insert, on replace, on remove, or on despawn as different functions. The functions for us are not that complicated. They just log out a message, and that's about it. They're logging out the entity it's called for, the source code line, actually, that triggered it, and which of the hooks it's actually running for. So our program then is fairly straightforward. In the last few days, we've already gone over the spawn APIs and relationships, so you should be used to seeing commands.spawn here. In this case, all we're doing is commands.spawning an entity with the example hooks component. In this case, I've included some numbers here because it will be useful later for us to determine which component is the one we're actually looking at. And in this case, we've grabbed the entity ID. So if we look at the types here, ID is an entity, and then we do a series of commands, right? We get that entity and we insert a component, we get that entity and we remove components, we try to remove it again, we insert it again, and then we despawn it at the end. So the first thing to note is that all of these happen later, right? We've got a startup system here. It's got access to commands, and we are executing a series of commands which happen after the end of this function. So if we log out empty lines in between these commands, all of those are going to fire first because all of these commands happen later. This whole function will finish, and then these commands are going to run. All of these get added to a command queue, but we're not going to talk about the details of the implementation. We're just going to say they happen later for now. You can think of later as basically immediately after this system ends. So if we look at what's happening here, we've got 5 events, right? Add, insert, replace, remove, and despawn. But all we're doing is inserting and removing. At the end, we do despawn, and at the beginning, we do spawn. But even so, that's still only 4, right? If you look at the sequence that the hooks are actually executed in, they're all executed for the same entity, that's 6v1 in this case, but you can see which line caused them here. So on add was caused by line 14, that's the spawn command here, and then on insert below it was also caused by line 14. So if you spawn an entity with a component, you will fire on add and then on insert. And these orderings are well defined throughout all of these other events. So when we try to insert again on line 16 here, on replace fires and then on insert fires. All of these are pretty intuitive except for on replace. On add fires when you first add a component, on insert fires anytime you would see a dot insert, on remove fires when you remove the component, and despawn fires when you, well, despawn the component, which also ends up removing that component. On replace is the only outlier here. That's a little bit unintuitive, but we'll see why in the next example. So hooks, what are they useful for? Well, one of the things is that you can get the values of the component that is being added, inserted, or removed inside of these hooks. So we've changed our component hooks here to be able to access the value of the component that is being inserted for the entity that it is being triggered for. If we look at hooks, we see they take two arguments, a world, which is a deferred world, which is notably different than a regular world, and a hook context. The hook context really contains the entity that we care about, the one that it got triggered for. So since this output gets a little bit longer horizontally, I will make this a little bit different of a layout so that we can see that. So when we log on add, we get access to a deferred world. The only difference between a deferred world and like a regular world is that you can't do structural mutation, but you can get access to commands and run them. So it's not like we can't do anything here. But for now, all we're doing is getting the component value for the hook that was fired. So we use the world to get this component based on this entity. In this case, we're unwrapping it because this is a hook, this component will exist, and then we're logging that out. And this is what we're doing for all of the hooks at this point. So if we go back up to the code that is actually running here, the reason I ended up putting in these values is so that we can talk about what is actually happening when these things are getting added and inserted, but specifically replaced. So if we look at the replace output, right, we spawn an example hooks component with the value 0. And then while that entity still has the component on it, we insert the same component again with a new value. That triggers on replace, but it triggers such that we see the old component value. So if you want to think of on replace as kind of like an on pre-insert, where the value hasn't changed yet, but it's going to. All of the rules for when all of these hooks can and will fire are in the documentation. So if you go to the component hook struct in the docs and you click on the left on add, it will tell you basically everything you need to know about on add or on insert or on replace, for example. And if you run this example, you can see all the component values as they propagate through, right? And again, I've left the line numbers in here. So if we wanted to see the first remove, that's line 19, that triggers this on replace and then that on remove. And then line 20 fires and there's nothing to trigger. So we actually don't see anything from line 20 because there's no component to remove. And then line 23 doesn't insert, which means we see on add because it didn't exist previously, and an on insert, and so on and so forth until we get to 26, which fires despawn, replace, and then remove. So hooks are really interesting because hooks are basically restricted to these 5 events, and they're restricted to these 5 events for performance reasons. Hooks can form the basis of other features in the ECS or in Bevy in general. Things like relationships can be built on top of component hooks. So as far as use cases, component hooks can be used to maintain indices or indexes such that you always know when any value was replaced or inserted or added or removed. Now you'll notice that there is no on mutate. That doesn't exist. So if you want to use hooks to maintain an index, you either need to take advantage of the new immutable components, which makes it so that you can't mutate, or you just need to either not care about the mutation or something like that. Or you can just, make sure that you never do that. So if hooks are restricted to these events for performance reasons, so people can't extend the list of events that need to be checked and fired, then where can we do that? Because that's super useful, right? And that would be observers. So we'll start looking at observers by looking at the same 5 events. In this case, we've got global observers, which we'll talk about in a second, for on add, on insert, replace, remove, despawn, the same events, right? The code here is also the exact same. We're still doing the spawn, the insert, the 2 removes. The component is the same, except we've removed the component hooks, notice. And observers are written like this. The trigger always has to be first. So in this case, we're triggering in the on add event for the example component. Now the right-hand side can be a bundle of components, but we're not going to talk about that today. And you'll notice that there's a huge difference in the way that we get the value of example component for this triggered event. In observers, you get to use the same kind of system dependency injection that you're used to all over the rest of your Bevy app. So as long as trigger is the first system param here, then you can use query, you can use trigger.target, which is the entity that this event was triggered for, and we can get that from our query, and we'll get that value the same way as we do in every other system. So observers can be ergonomically very similar to just any other system that you're writing, which makes them a very attractive potential option. And if we look at the output for the observers, we can see that this is basically exactly the same, right? We've got the on add, we've got the on insert, we've got the replace, and so on and so forth. So something that is kind of like immediately interesting is what happens if you have hooks and observers defined. So here we have all of the observers that we just looked at. We've got the same code that we've been looking at. And we've also got all of the component hooks. Now, the hook that we are actually calling here is a little bit different in an effort to kind of reduce the amount of code here, because I left, as you can see, the observers as a one-to-one. Like this on remove is basically a copy of on despawn, except I've changed the label here. I left all of those because if you run this, I want you to be able to play with it, but I've collapsed all the component hooks since we've stopped talking about those. So that's what this is. This is just a generic function that takes a hook name string slice and returns the function that will be called as the hook. But otherwise, this is doing the same thing as before. Notice that I have added parentheses hook for all of the hook labels, and I've used warn instead of info. So we are looking at all of the same code, except that we are looking at all of the hooks firing and all of the observers firing. This is interesting because if you look at on add, you'll see it fires twice now, once for the hook and once for the observer. On insert similarly fires once for the hook and then once for the observer. But if we look at things like on replace, it fires the observer and then the hook. If we look at despawn, it fires the observer and then the hook. Similar to remove, it fires the observer and then the hook. This is because hooks are considered the basest source of truth for these events. So if something is being inserted, they are the first thing to be called. And if something is being removed, they are the last thing to be called. So notable that there's a slight ordering difference in case you have both hooks and observers for the same components. So now we're going to deviate a little and just keep talking about observers from here on out. There are roughly two kinds of observers we can use, which are generally referred to as global and local observers. To add a global observer, you use add observer on the app. It still takes a trigger. It's still the same function signature. This will just accept any on add, for example, component that fires anywhere in the application. Meanwhile, if we look at our startup function, we've now spawned 3 different entities. We haven't spawned them with any components, which doesn't really matter. They're still entities. And we are doing .observe with an on add observer. So here you'll see the exact same code that we're used to. It's got a trigger. It's on add for the example component. So this will fire whenever we have on add for the example component for the entities that we're observing. So in this case, on add will fire for each of them. You could have a separate observer on each entity and it would be a separate function call. And if we look at what happens here when we insert something on each of the entities, the global on add gets called and then the entity's local observer gets called. The global one gets called, then the local one. The global one, then the local one. In general, I would generally prefer global observers to local observers. This is slightly for performance reasons, but you're still going to find local observers pretty useful. For example, if you want to observe a button click, you don't really need a global observer if that button exits the app. I know Avian just introduced in their main branch an observer for on collision start and on collision end, which is generally a local observer for a specific entity. So you don't need to shy away from local observers, but if you can write it as a global observer, that would be my default. So we've talked about on add, on insert, on replace, these pre-existing events that Bevy kind of provides for us. But we can also have custom events. And these observers are written in exactly the same way. So my event here is our event. We've defined a custom event. If we scroll down, we can see that my event has a field n, which is a U32, and we've derived event for it. The observer for listening to this event when it fires is the exact same as the other observers. When it triggers, we're just triggering for my event. And in this case, we have a global observer as well as a local observer. And in this case, we're doing the same thing where we spawn empty and we have the local observers applied to each of these entities. So this brings up the interesting question of if you have local and global observers for these events, you probably want to be able to trigger them in different ways. And we can. We've got 2 functions here. One is trigger targets and one is trigger. So if you use commands.trigger targets, you can fire your event at a specific entity. So if we look at what's going on here, we've spawned our 3 entities, and then immediately I've triggered my event with n equals 0 for the first one. So what happens is we get a global handler for that event because we have the global observer, and then we get one for the local observer. So this on my event fires. You can trigger targets for more than one entity at a given time. So if we trigger targets for all 3 and we look at the sequence that happens here, it first fires the global and then the local for each of the entities. So it fires the global, that still has access to the target. So it still has access to the entity that the event is firing for. It's just registered at a global level. And then the local observer also fires. And finally, we can have events that don't need to be triggered on any entity. They can just be triggered in general. Maybe you have a single player game and there's a point being scored. If we use commands.trigger, we can trigger events that don't need to target any specific entity. And when that happens, you'll see that the trigger target, if we go up to the global handling here, we're just checking trigger target for this target value. That target is placeholder. And placeholder is interesting because that comes from entity placeholder, which is just an entity ID with a placeholder value. So the trigger.target function still exists, even though this is a global observer, but the target will be equal to placeholder if it wasn't targeted at anything. And you can see that we only get the single event firing because we're not targeting this to any specific entity, so only the global observer catches it. Now, observers can be used for many different things, and they're very flexible. So in this case, I've already run the program on the top. We have a global observer here called onMyEvent. onMyEvent waits for my event. My event is an event with a spawn n times field that is a usize. We're going to log out every time this observer is called. We are going to get that spawn n times value from the event, and we're going to do a checked subtraction of 1. So since this is a usize and we're going to subtract 1, if we hit 0 and we subtract 1, that would underflow. Checked subtraction allows us to check to see if that's going to happen, and if it does, then we'll just stop. We'll return from the function. This is important because what we're actually going to do here is recurse, and we're going to recurse by triggering the observer again. So if you look at the output here, you can see that spawn n times comes in with a 4, and then it fires with a 3, and then fires 2, 1, 0, and then says done recursing. That's what's happening here. We do a commands.trigger with the number 4 inside of the event. Our observer fires. It gets down to trigger the same event with the value -1. And the really interesting part here is that we start off with 2 triggers here, but the first one and all of its recursive calls completes before the second one even starts. And that's kind of a key feature of observers. If you call more observers, if you queue up more commands inside of an observer, those commands are handled before moving on to the next items in the queue. This makes it really easy to guarantee that things that you want to happen will happen without having to stuff everything into the same function. Because if we had some complicated functionality here that we wanted to trigger a couple of observers for, we could trigger them all, they would all run to completion, and then we would get the next set of events in the command queue. So this can be fully recursive in that if you don't check for the recursion, you will get a Stack Overflow. So for example, if this was an addition and we've got a usize, this won't run for all of usize because eventually it'll Stack Overflow. The number of observers that you can call recursively is still pretty high, but there is a limit. So that brings us to our next example, which is kind of like recursion, but is actually event bubbling. So here we've got a new setup. We've got startup and then trigger event, and we've got a global observer. Global observer is looking again for our custom event. Our custom event is a little bit different now. Our custom event includes auto propagate in the attribute macro, and we've defined a traversal component, which we'll talk about in a second. The 2 systems that we have running, startup runs first, which builds this kind of very highly nested hierarchy. There aren't a lot of interesting components on here. We just have a bunch of names, but it doesn't really matter. These can be as complicated as you want them to be. I've just kept them very simple. And on the most deeply nested child entity, we have this marker component. This marker component is not very interesting. It is literally a marker component. There's no fields on it or anything. After we have spawned this in, the next system to run is this trigger event system, which will look for the entity with the marker on it and trigger an event for that entity, and just for that entity. It did not trigger multiple events here. It didn't trigger for multiple entities. It is only triggering for the deepest entity in the hierarchy. There is also no recursive code in our observer. All it's doing is logging out the event. But if you look at the output up here, you can see that it triggered for a target, and then it triggered for another target, and then it triggered for 2 more targets. So it triggered for 4 in total, which is interesting because we triggered it for this one, and that means it triggered for this one, and then this one, and then this one, which is 4. So it triggered for the entire hierarchy. It bubbled its way from deep, nested, all the way up to the root and fired for every entity. And that's what we're looking at when we look at traversal. We're defining the component that the propagation, which we've enabled by default, is going to use to traverse the hierarchy. So in this case, we've used child of. Child of is built into Bevy. This is the child of children hierarchy relationship that you're already used to seeing. We've talked about it in other recent videos. And we've turned on automatic propagation for this event. So when we fire it, it will find a child of if it's on that entity. It will use it to get the parent. It will fire for the parent. And then it will keep following that until it can't follow it anymore. Now, there are two other ways you can do this. You can do this manually. You don't need to automatically propagate. There is a propagate function that you can call in your observers. And you can also cancel propagation. So you don't have to let it keep propagating either. This can be very useful for things like picking, either mesh picking or UI picking or something like that. On the web, we have event propagation and event bubbling. It's a very commonly used thing. So if you're familiar with the web, you'll be familiar with that use case. Imagine that our deeply nested entity had a mesh on it. That mesh is going to be the only thing that you can pick if you have mesh picking, but you might want to run the observer on the root. There could be an arbitrary number of meshes inside of this hierarchy, so you might want to let that bubble up. You could put an observer just on the root and handle the event only when it gets to the root. Remember, this is a global observer, but it doesn't have to be a global observer. It can be an observer anywhere in this hierarchy. So let's talk about that component again, right? We previously used traversal for child of, and child of, as we know, is a relationship that is built into Bevy that is implemented for us. In this example, we've built our own relationship. It looks a lot like the same relationship as child of and children, but this is totally custom, something that we've invented, right? We have inventory and item of. So this could be a player's inventory. This could be the inventory in a chest. This could be anything's inventory. This could be an NPC's inventory and so on. So unfortunately for our inventory, it's going to be located in a wooden chest. And again, unfortunately for that wooden chest, we're going to have a lot of flammable things in our inventory. So note that we have some paper here. This is very dry paper. It's got a flammable component on it. Say the sun got too hot or it got too close to a wizard casting fireball, and the paper inside of the chest is going to catch fire. So we're going to fire the catch fire event on the entity that had the flammable component on it. And because we've defined this as automatically propagating, and because we've chosen the item of component, which is a relationship, to traverse with catch fire, if we look at our output, when the paper catches fire, it also propagates up and fires catch fire on the chest, at which point we can decide, is this chest dry enough to also actually burst into flame? So bubbling and propagation can be used for any of these relationships. This is no longer a transform or child of children based relationship. We've used the related macro to spawn our custom inventory relationship target with a number of items inside of it, and we can target those items with events, and those events can raise to the level of the container. And that can happen either automatically, like we were talking about with auto propagate, or it can happen manually. And observers, of course, in this example, we have this observer returning a result. It returns a result because we're querying for name. And if we do names.get, the target for this global observer might not have a name component on it. So we might have to return an error. So that's quite a bit about hooks and observers. Hooks have about 5 events. They're high performance. You can only define one of them. If you try to push more hooks into something, into a component, it will error out. Observers, far more flexible, still very performant. So you don't need to worry about the performance at all. It's just that hooks are designed for high performance and thus have a limited event set that doesn't expand. Whereas observers are more flexible and end users can define their own events, their own propagation behavior, and as such are usable in a wider array of use cases. You can use hooks and observers to maintain indexes. When different components get inserted or removed, you can update those indexes. And if you use immutable components, which is a completely different feature, you can even ensure that those indexes are guaranteed to be up to date, because the only way that you would be able to change them is by inserting, which you can listen to with a hook or an observer. So that's it for observers today. I have a feeling this video is going to be pretty long already, so I'm going to stop there. If you have more observer questions, leave them in the comments, and I'll see you in the next one. Have a great rest of your day.